just preparation for the exam. I did send out a video pointing out some resources that are available on Canvas between videos and practice quizzes and things like that. There are old exams that you can look at. So if you need help figuring out what to do in order to prepare for the exam, take a look at the video that I sent a clip. Or say again. Hold on onto it until the end of the semester, because I'll give you several of them and just turn them all in at once.
Okay.
Yeah. So if you had picked up one of these things and I said I'd give a little bit of extra credit for it, you're going to collect them all and then at the end of the semester turn them in, and that way I can just look at them all at once. That helps me with grading. Okay. So any questions? Okay, so as far as thinking about a study guide, what I would give as a study guide is basically those objectives that are at the top of each overview page on Canvas. So that's already there for you. The ones that are in bold are the most important ones. And then as you go and look at old exams that I have done, you'll be able to see the parallels between what the objective is and how it shows up on exams. And I think that's kind of the best way for me to help you to prepare for yourself. Okay, so we had just started talking about balancing equations on Friday. I know this is something that for some of you, you've seen it before, and for others, you have not. So, you know, if it's old news to you, sit back and enjoy the ride. The rest of us will be figuring it out. After that, we are going to be doing some math. So if you have your calculator with you, you may want to pull that out. Okay, so our rules for balancing equations were basically that you can't add any new chemicals or change the chemicals that are there. So we weren't allowed to either put a little 2 next to this, that would change the chemical, or add a little oxygen. You also can't delete chemicals. But we can change the coefficients. That's pretty much all you can do. Change the big number, but it has to be positive, has to be whole, and then we want to have the lowest possible ratio available. Okay. So somebody asked me, well, what if you don't have the lowest ratio? So let's say on a test you gave me 4, 2, 4 on this instead of 2, 1, 2. Then what I would probably do is this would probably be worth 3 or 4 points, and I would just take 1 point off for it not being the lowest possible ratio. So you wouldn't lose all your credit, but you need it lowest possible. Okay, so what I want to look at is how can we go about balancing things? Now, if I have something that is pretty simple, like the water scenario, I can usually eyeball it and be like, what works? I call that the guess and check method. But most of the things we're going to have are going to have compounds instead of elements in most of the places. And there might be too many that guessing and checking doesn't work real well. So this is a method that I like to use. There are lots of different methods out there. If you have one that already works for you, by all means, use whatever works for you. You can always look on YouTube. There are lots of different videos showing you how to balance equations and things like that. So, you know, try out some of those different methods. If you just Google, show me how to balance equations or practice balancing equations, there are lots of things available for that. What I like to do is to figure out where I do want to start and where I don't want to start. So the first thing I want to do is pay attention to, do the elements appear more than once on each side? So on my reactant side, carbon is only in CH4, that's methane. Hydrogen is only in the methane, and oxygen is only in the oxygen. But if I look on the product side, the oxygen is in 2 different chemicals. And that means that changing either one of those is going to change my oxygen. So if I start by balancing the oxygen, I'm just going to have to redo it. So I don't want to start there. The other thing is, if I do have a pure element, like oxygen is a pure element, If I do that last, I can change oxygen without changing anything else. So I want to save that for last. All right. So in order to balance the equation, I'm going to add a coefficient to one side of the equation. So usually however many atoms are in the element on one side, that's what I'm going to put on the other side. So my carbons are already balanced. You can see I have one carbon here and one carbon here. So I don't really need to do anything. But if I look at the hydrogens, on one side I have 4 and on the other side I have 2. Okay, so this is where I'm going to apply this rule. I'm going to add a coefficient to the water to show me that I have 2 of those molecules. So remember that that number, the coefficient, applies to the whole molecule. So it's like saying I have this as a water molecule and this as a water molecule. So not only do I get 1, 2, 3, 4 hydrogens, I also get 2 oxygens. And I have to keep that in mind when I'm balancing things. Okay, so I'm going to put that 2 in front of the water. And now the hydrogens are balanced. Okay, then I go on to my last element, which is oxygen. And on one side, I only have 2 oxygens. On the other side, I have to count both places. So I have 2 for the carbon dioxide. And then since I have 2 water molecules, I have 2 more. So I have a total of 4 oxygens on my product side. So what can I put in front of the O2 in order to give me 4 oxygens on the reactant side?
2.
A 2. All right, so the next thing is to make sure that I have the lowest possible coefficients. So usually if this is a problem, it's because I have all even numbers. So if I had 2, 4, 2, 4, then I would need to divide everything by 2. That's the most common thing. Sometimes it happens with 3. So 3, 3, 6, 12 or something, and you need to divide it 3. So you just want to check for that. If any of your coefficients is 1, and remember 1s are invisible, then you can't go any lower than 1, right? So I can't get any lower than this one. I can't get any lower than this one. So I should already be in the lowest possible coefficients. Yes.
Take a picture of that real quick.
There's one more thing on the slide, but yes.
Okay.
These slides are also on Canvas.
Oh,
so
okay.
the whole thing is called Balancing Equations. So if you go to the Chapter 3 overview, it's available for you. But if you want to take pictures, I know some people just like having it on my phone, that's fine. Okay, so then the last thing we do is double check on each side of the equation. So how many carbons do I have? I have 1 carbon on each side. How many hydrogens do I have? I have 4 hydrogens on the reactant side that are easy to see. And then on the product side, I have to do a little math. 2 times 2 gives me 4 hydrogens. Okay. For my oxygens, I have 2 times 2 on the reactant side. On the product side, I have 2 that are in the carbon dioxide, but then I also have to count the second chemical where there are 2 molecules. So I have 1 oxygen, 2 oxygens there. So a total of 4 oxygens. Okay, so I've double checked to make sure that that is balanced. One thing that is very helpful is that people will put a vertical line below the arrow so they can make sure they're separating reactants from products. Now, in this case, it's pretty even. So the middle is where you would draw that vertical line. But if you had, say, 2 reactants but 4 products, then the middle wouldn't be where you separate the reactants from the product. So having that vertical line can kind of visually help you separate where you're counting things out. Okay, most of the questions I would ask you would be something along these lines, and they're generally worth 4 points. I'm going to go through a couple of harder examples just so you can see what to do with them. But if something like these showed up on your exam, they would be worth extra credit. All right, so the last one we had methane with oxygen, giving us carbon dioxide with water. This one looks very, very similar, but instead of methane, which is CH4, we have ethane, C2H6. And so we are going to start out very similar. but our carbons aren't balanced to begin with. Now on this sentence, I'm talking about balancing two things at once, so that throws people sometimes. So I both need to balance the carbons because there are two in the products, or there should be two in the product side, and hydrogens, I need 6 in the product side. So clearly I need to put a 2 in front of the carbon dioxide. What do I need to put in front of the water? How am I going to get it? 6, a 3. Okay, so at this point, I have balanced the first chemical with the carbons and hydrogens on the product side. I've changed coefficients on them. I haven't done anything with the oxygen yet. It's not balanced. Okay, this is where this gets a little bit different from the last problem. If I start counting up the oxygens on the product side, how many do I get? Try counting again. 7. Okay.
Oh, yeah.
So the reason I get that is there are 4 coming from here and there are 3 coming from here. That's going to give me my 7. Is there a number, a whole number I can put in front of the oxygen so that I have 7 oxygen atoms? I can't do a whole number there, but I need to do a whole number. So this is what I call an even-odd conflict. Since this has 2 here, I'm always going to have an even number on the reactant side, but I've got an odd number over here. So the way I'm going to change that is to change all of my coefficients to even numbers. Okay, so when I say multiply through by 2, every coefficient that I have already changed, but only those. I'm not going to do anything with the oxygen. I'm going to multiply by 2. So I'm going to say there's an invisible 1 in front of the ethane, the C2H6. So I'm going to multiply that by 2. I'm not going to do anything to oxygen. There's a 2 in front of the carbon dioxide. I'm going to multiply that by 2. And there's a 3 in front of the water. I'm going to multiply that by 2. Okay, so that's what I mean by multiply through by 2. And so I put a line next to the oxygen just to emphasize we haven't done anything with it yet. Still need a number. Now, the reason I multiply everything that I've already balanced is to keep those things balanced. Okay, so now I still have 2 times 2 is 4 carbons and 4 carbons here. And I have 6 times 2 is 12 hydrogens, and 6 times 2 is 12 hydrogens. Okay, that's why I do that. Now, how many oxygens are on the product side? 14. So can I change the coefficient in front of the oxygen so that I have 14 atoms? Yeah, I can put a 7 in front of it. Okay, so like I said, if this is a little bit confusing, don't panic, because this is one that would be worth bonus points. Okay. And I do give partial credit. So if you can get part way and just can't figure out the oxygen, you'll get some credit there. All right, anybody still need this slide? Okay, so we're gonna try another one. This one's even a little bit more challenging. So if you like puzzles and you like challenges, I'm gonna try this one. Right. I'm gonna give you a second to try and get started on it, and then I'll walk you through it. All right, we probably noticed that our nitrogens are already balanced. So we don't have to do anything with that. And then we go to try and balance our hydrogens and we run into a problem, right? Because on one side I have 3 and on the other side I have 2. So far I have looked at the first chemical of the reactant and the first chemical of the product. And I've said those can both be 1s. And so I'm going to multiply those by 2. Okay, so that way I will have 6 hydrogens on the reactant side. And so on the waters, how many water molecules do I need to get 6 hydrogens?
Multiply by 3.
By 3, yeah. So a couple of people giving me 3 fingers. So our nitrogen was balanced. We see that even odd conflict. And so we fix it by putting the 2 in front of the ammonia and the 3 in front of the water. And then we can put a 2 in front of here to make sure the nitrogens stay balanced. Okay, so we've gotten ourselves out of that even odd conflict. So now we're going to go back and say nitrogen is balanced, hydrogen is balanced. How many oxygens do I have on my product side? 5. So yet again, I have an odd number of oxygens, but this chemical on the reactant side has to be an even number of oxygens. So all of the coefficients that I've already changed, I'm going to multiply those by 2. Okay, so before I address the oxygen, I'm just going to double check. 4 nitrogens here. 4 nitrogens here. Still okay on nitrogen. 4 times 3 is how many hydrogens? 12. And over here, 6 times 2 is 12. So I'm good on the hydrogens. Okay, how many oxygens do I now have? 10. So I have 4 coming from the nitrogen monoxide and 6 coming from the water. So how many or what coefficient should I put in front of the oxygen in the reactants? A 5. Okay. So again, that's probably trickier than you would see on an exam. But I wanted you to have that opportunity to see how you can fix a problem when you run into it. Okay, so the next thing that we're going to do is we are going to look at a few examples. And so I want you to, oh, I forgot. We need to go back and double check that we have the right number of atoms on each side, but I did this verbally. So we have 4 nitrogens. We have 12 hydrogens on both sides. And then on one side, we have 10 oxygen. The other side, we have 4 and 6. So we are good. Do I have the lowest possible ratios? So here I don't have any invisible 1s, right? But there is nothing that I can divide 4 by that I can also divide 5 by. So I can't make them any smaller. So we call that mutually prime, if you remember that number or that phrase from math class. All right. So one thing that sometimes people will do just to make sure is they might draw out the molecules so they can count them up, or even just write out all of the elements. So I might write HO for H2O, HO, and then count. I have 1, 2, 3, 4 hydrogens. I have 2 oxygens. If that is helpful to you, by all means, draw them out. If it is not, I do not need to see it. Okay. Okay, so here are some samples to try. I'd like you to look at the third one for zinc, because that's probably the easiest one on the page. There's a big space in here because I just hit tab when I was putting on the computer. Don't forget the hydrogen. You'll need that to balance it. And then after you figure out zinc, then we can go back and try the others. So if that one comes really easy to you. Try all three of them. I'll come around, and if you have questions, you can ask them. Zinc is balanced. Hydrogen is by itself, so we need chlorine first. We need 2 chlorine, so we put a 2 here, and then that balances the chlorine. Okay, so let's go back to this one. So we've got hydrogen and nitrogen, pure elements, and then we have the ammonia over there. So we could balance the nitrogen and put a 2 here, but I'm noticing that I've got a 3 here with this hydrogen. So that's letting me know maybe I need to be multiplying things by 2. So let's look at this and this. Well, yes, I do have an odd conflict. So I'm going to put a 2 here. Now we're back. What do I need in front of the hydrogen? The 3 in order to balance those hydrogens. And then what do I need in front of the nitrogen? All right, so I have 6 hydrogens and 2 nitrogens, and I have 2 nitrogens and 6 hydrogens. All right, so do we have an even odd conflict in this one that we need to deal with? Yeah. So we have an odd number of oxygens. So I'm going to multiply this by 2. These are both pure elements, so I can save those for last. Okay, so now what do you want me to do? I'm sorry, I didn't hear you. Put a 2 in front of which one? The product, there's already a 2 in front. You want a 3 in front of the oxygen? Yes. Okay, so that gives me 6 oxygens here and 6 oxygens here, and a 4 in front of the aluminum. So 4 Als and 4 Als. Okay. Okay. So I want to save hydrogen for last because similar to the oxygen, and this time it appears twice in our products and is and pure element there. So is carbon balanced? Okay, is oxygen balanced? No. So what do I need to do?
Multiply the water by 2.
Okay. So does that change what I have to do for the carbons?
No.
No, because I didn't change any carbons. Okay, so now how many hydrogens do I have over here? 8, because I have 4 hydrogens here and 4 hydrogens here. So what do I put in front of the hydrogen over there?
4.
4. So that'll give me 8 hydrogens. Okay. There are a lot of websites that will either walk you through balancing equations or will give you examples that you can practice with. So if this is something that isn't clicking right away, I recommend just Googling practice balancing equations, and you should be able to find plenty of opportunities to do that. And as I mentioned, I did move my office hours this week so that I have office hours both today and tomorrow. So if you want me to go through it with you or just check your work, I can do that as well. Okay. All right. So next thing, going back to our empirical formulas and trying to find those, we kind of did the easy examples. But sometimes when we get to the step where we're dividing by moles, we end up with something that isn't a whole number. So far we divide everything and we get a 1 or we get a 2 or we get a 3. But now we're going to look at an example where we don't. So chromium is one of the metals, the transition metals that can have a number of charges. And so we don't always know what the formula is going to be. So a certain chromium oxide is I'll put a little question mark here because we don't know the charge. 68.4% chromium. And 31.6% oxygen. Okay, so we know that we need a mass, and then we need the formula mass for each of the elements, and we're going to change that into moles. So I like to start with 100 grams because I can easily find the mass of chromium by using the percent. So basically I'm just changing the percent to grams. We've used oxygen a lot, so you might remember the formula mass for oxygen. It's 16.00 grams per mole. Now, on some periodic tables, it says 15.999, but if I round that to 2 decimal places, it becomes 16. I want to keep at least 2 decimal places so I don't lose significant figures. What about chromium? Okay, 51.996 grams per mole. So I can leave it like this because that's more than 2 decimal places, or I could round it, and similar to with oxygen, this being closer to or more than 5 would round this 9 up, which would round this 9 up. So we could write 52.00. That would also be appropriate. Do not just write 52 because then you might forget that you actually have 4 sig figs. Okay, how am I going to get to moles? What do I do with these 2 numbers? Divide. So 68 divided by 51.996 and 31.6 divided by 16. And please remember to bring your own calculator to the exam. I will have a handful of extras, but I don't have a whole classroom set. And you will definitely want to know how to work your calculator, especially when we get to doing things in scientific notation and logs and things like that. Okay, so how many moles do we get for the chromium? 1.315. Now, if I'm paying attention to my sig fig rules, how many sig figs do I get for my final answer?
5.
I used a smaller amount, right? But I like your enthusiasm. Thank you. Okay, so I should just report 3. And then I've got this 5 here. So this is where there's the, well, there's a rule, but I don't care. You round it to the even number. So we should put 1.32. But if you rounded it down to 1.31 and did your calculations that way, I would not count off for you. It's just sort of arbitrary that we say we round it to the even number. Okay, and then over here, what do we get for the oxygen? 1.75, but did we round that one too? Yep, so 1.975, also needing 3 significant figures. This one, we would round to the 8 because 8 is even, so 1.98. These are both moles. And now what do we do?
Divide the smaller one by itself.
Divide the smaller one by itself. It is very common for people when they get to this point and they see, oh, that's almost 2, I'm just about done. And forget that they need to do this part here where you divide by the common number. So don't forget, we got to divide by the smallest, 1.32, which is going to give us 1 here, and 1.32, which, what does that give us here? 1.5. Okay, so we don't have a whole number. We have 1.5 oxygens for every chromium. Now you might be able to, in your head, kind of figure out, okay, I know what that ratio is, but if you can't figure it out in your head, or if it's like a weird number, you kind of need to know what to do, okay? So, I'll put CR here, O here. When we don't get a whole number, okay, so we are going to look at the one that has the decimal. So this one has the 0.5. We're going to ignore the chromium because that was already a whole number. We're going to look at this one that has a 0.5. And we're going to go back to the days when we had to memorize fraction, decimal, percent. All of these things are related, and say to ourselves, 0.5, was that one of those really easy fractions? So was it? 0.5, what is it? 0.5 is 1/2, right? Okay, so 1.5 is going to be some fraction halves, happens to be 3 halves, but it's a half, right? This is a half. So when we see something that is one of those decimals that turns into an easy fraction, we multiply by the number that's on the bottom of that fraction. So I'm using x for whatever happens to be before it, but x 0.5, we multiply by 2. X 0.333, what's 3333? 1/3. So we would multiply by 3. Similarly, if we had x 0.667, that's 2/3, right? So we just multiply by the bottom part, the 3, okay? And if we had x 0.75, what's that?
4.
Yeah, we multiply by 4 because it's 3/4, okay? Ones that maybe don't pop right out at you, but do show up in this kind of thing, if it ends in 0.2, 0.4, 0.6, or 0.8, this set you multiply by 5. And that's about as high as you would need to go. If you can't remember what to multiply by, just start plugging in 1.5 times 2. And if that didn't work, try 1.5 times 3. And then try 1.5 times 4 until you get a whole number. Okay? Whatever works to give you a whole number here, you're also going to multiply the chromium by that. Okay? So multiply all molar ratios. Remember, these were our molar ratios. Moles of chromium, and moles of oxygen, moles of chromium. We're going to multiply by that same whole number, because I'm not going to have the same ratio if I multiply this by 2 and this not by 2, right? I want to keep them in the same proportion. So this is saying that 1 to 1.5 is the same thing as 2 to 3, right? So if I had 1.5 oxygens for every chromium, then for every 2 chromiums, I have 1.5 and 1.5, which is 3. Okay, so I'm multiplying this by 2 and this by 2. Okay. All right, last thing I want to look at is something that shows up in your homework problem. Sometimes we get questions where it says, okay, I know the empirical formula, and I figure out the molecular formula. So No. If we know the empirical formula and we know the molecular weight, we can figure out what the molecular formula is. So for example, this happens a lot with organic compounds. Organic compounds tend to have lots of carbon, hydrogen, and often oxygen, okay? And because they have lots of those, they can combine in lots and lots of different ways. And so we can get lots of compounds that have the same empirical formula. So if the empirical formula is CH, and the formula mass is somewhere around 25, we should be able to figure out the molecular formula. So the first thing we need to do is find the formula mass of the empirical formula. Okay? Okay, so what is the formula mass of CH? Carbon is 12.01, H is 1.01, 13.02. Okay, so that tells us 13 is not the same thing as 25, not close. So this is not the molecular formula, okay, because they don't have the same formula mass. But then I figure out, well, how many times does this go into that? How many times can I add up 13.02 to get something really close to 25? Figure out how many times the formula mass of the empirical goes into the formula mass of the molecular. Okay, so this one, not too hard. I can just say, well, what if I double it? 26, is 26 pretty close to 25? Yeah. So I'm going to say CH times 2 is 13.02 times 2, which is 26.04, which is not too far from 25, okay? So then the last step is to say, well, what did I multiply by? I multiplied by 2, and I'm going to multiply all of the subscripts by that, okay? So C2H2. So what if I do the same thing, the empirical formula is CH, but this time, so new question, different compounds, the formula mass is somewhere between 70 and 80. See if you can figure out what that would be. Does anybody think they know how many times 13 would go in? Tristan, what do you think? 6. Okay, so if it is 6, 13, let's try this, 13.02 times 13.02 times 6 is going to give us what? 78.12. So then what would I write as my formula? C6, H6. let's try doing a different formula. Let's say we have CH2 and the molar, the formula weight, formula mass is between 55 and 60. So what's the formula mass of CH2? Is it still 13? It's 14. What do you got, Tristan? 4. So that's going to give us around 56. Okay, so times 4. So then I would say C4H8. Okay. All right. Don't forget you can use a 3x5 note card on your exam, either side, whatever you want. I recommend some chemistry.